Welcome to Engineering Mechanics Statics, Chapter 3, Rigid Bodies and Equivalent Systems of Forces. Okay, we're going to go over some new things in this chapter. We're going to introduce the concept of vector or cross product. The text will refer to it as a vector product. Most people refer to it as a cross product. We're going to introduce the concept of a moment, and in that we're going to talk about Varignon's theorem in dealing with moments. We're going to introduce scalar or dot product. We're going to introduce couples, and we're going to finally discuss reducing a set of forces into a force couple system. And this is why we're talking about the other things leading up to this point. Okay, forces. Let's talk about forces. Okay, internal versus external. Well, forces can be classified as either internal or external forces. In this class, honestly, we're mostly going to ignore internal forces. Okay, external forces are those that are shown on a free body diagram. So consider this truck, right? You have this truck and this thing is being pulled by some people with a rope. Well, if you were to draw a free body diagram, you have the reactionary force at each wheel, you have the weight of the truck being pushed down, and you have the force here. Those are all external forces. Clearly, this force, these wheels, this thing is going to want to bow like that because if it was not a rigid body, and again, in the real world, nothing is truly rigid, so you're going to have a little bit of bow in the car. You're going to have different internal forces, but we are going to talk about external forces, and those are the ones that are showing on the free body diagram. If unopposed, external forces can impart translation, rotation, or both, and so that's why we're going to consider or concern ourselves with those forces. Now we have something that's called the principle of transmissibility. The principle of transmissibility is it's saying that conditions of equilibrium or conditions of motion, either one, they're not affected by transmitting a force along its line of action. So what does that mean? It's saying if you have this potato and you apply a force here in this direction, there's no real difference if you were to apply a force here in this direction. Again, this is based on external forces. So when you consider external forces on this truck, for example, okay, if you have the force here and you're pulling it, or if you move that force to the back and you're pushing it, the conditions of equilibrium are not going to change. The truck is still going to accelerate or do whatever it's going to do. It's independent of where this force, not where this force applied, but if it's along its line of action. So anywhere along here, if you could somehow magically push from right here, it would have the same effect. Now, this principle of transmissibility often does not apply when dealing with internal forces. So let's look at this condition right here. We have this block, right? And you have two forces. You have one going this way and one going this way. Say they're equal forces, okay? So say P1 is equal to P2. Okay, well, the principle of transmissibility says we can apply these forces anywhere along their line of action. So let's take this P2 and apply it here at this point, okay? Well, if these are equal, there's nothing happening, so we're saying there's no effect on this. Okay, fair enough. Now let's come here. We have these same forces P1 and P2, but now whereas here it was pulling this thing apart, now it's squishing it. Well, we can do the same thing. We can take this P2 and move it here along the same line of action, apply it here, which says that it's nothing. Okay, so from an external perspective, from a grand scheme of things, is this thing going to move? Whether you're pulling on it in tension or if you're squishing on it in compression, either way it's not going to move. So for external forces, the principle of transmissibility applies, but for internal forces, clearly there's a huge difference between something being pulled apart or something being squished. But again, for this class, we're basically going to ignore this part. We just want to point this out, that this is not a generally true statement, but for external forces, this is going to work. Okay. Let's talk about a vector product or a cross product of two vectors. Okay, it's referred to as a vector product because the output is a vector. Most everywhere in math, you're going to see it referred to as a cross product. Okay, what is a vector or cross product? It's a vector product is of two vectors, P and Q, is defined as a vector V if the vector V satisfies the following equations. Okay, so following conditions. This is how it's defined. A, the line of action of V is perpendicular to the plane containing P and Q. So a cross product, the vector is always perpendicular to the plane containing the two vectors. The magnitude of V is PQ sine theta. So it's the magnitudes of the two vectors times the sine of the angle between the two vectors. And lastly, it has a given direction, and that direction is given by the right-hand rule. You put your right hand pointing in the, if this is P cross Q, you put your right hand and you point all your fingers in the direction of P, and then you close your hand toward the direction of the other vector Q, and where your thumb points is where the positive sense of that vector is. So if you put your hand here, P, and rotate it and close it towards Q, then your thumb, you notice, points up. So for a vector product, the direction is given by the right hand rule, so it's in this direction. So cross products, there's some things that you should know here. They're not commutative. So Q cross P is not the same as P cross Q. Because again, look at the right hand rule. If you start with Q and you put your fingers in the direction of Q and then you close your hand towards P, you have to turn your hand upside down in order to close your hand towards P. And once you turn your hand upside down, you'll find that your thumb is pointing downward, so that the direction is actually opposite. They are distributive, however, so P cross Q1 plus Q2 is, you can distribute that out, and it can be P cross Q1 plus P cross Q2. But they are not associative. So P cross Q, that quantity cross S, is not the same as P cross the quantity of Q plus S. Okay, so let's look at some of the rectangular components. So of vector products of Cartesian coordinates or regular unit vectors, I cross I is equal to 0. Let's just talk about that for just a second. Why is that the case? Well, I cross I, again, it's the magnitude of I times the magnitude of I. Let's come back here. It's PQ sine theta, right? So this is going to be 1 times the sine of the angle between the two. What is the sine of the angle between I and I? It is 0, sine of 0 is 0. Therefore, I cross I is 0. Same with J cross J is 0, and K cross K is 0. Now, the other ones, you're going to have the sine of 90, which is going to be plus or minus 1, depending on the angle. Well, the sine of 90 is always 1, but depending on if it's plus 90 or minus 90. And what you're going to find is I cross J is equal to K. So does this make sense? Look over here. I cross J, you put your fingers along the X direction, you close your hand towards the Y direction, and your thumb is pointing in the positive Z direction. So I cross J is positive K. I cross K, so now you put your hands in the I direction, and you close your hand towards the K direction. So the only way you can do that, and it's right here, is if you have your hand in the negative, has to be, your thumb is going to be in the negative K direction. So I cross K is equal to minus J, and so on. These are one of those things that you just want to understand why it is, but then you're just going to want to memorize them or know how to do the right hand rule. It's kind of comical seeing people at test time, but this is just the way it always works. You'll see people trying to point their hands and turn their hands upside down and point their hands in different directions and seeing which way their thumb turns. But that's how you do this. That is how it is done. Okay, so given that these are associative, you can multiply it out, right? Let's start with vector P. So Px in the I direction plus Py in the J, Pz in the K, right? Cross Q vector, so Qx in the I and whatnot. You can go through and you can do each one of these out. So it's going to be Px times Qx I cross I, but we just talked about I cross I is 0, so that goes away. Px Qy I cross J. Well, I cross J is positive K, so you look here at K, you have Px Qy. And you can work this all out individually, distribute them out, or you can express it as a determinant. And this is how I will do it in this class. This is kind of the common way to do it, is P cross Q can be expressed as the determinant where I, J, and K are the top row, and then you have the P vector, and then you have the Q vector. Now the order matters, because remember, Q cross P is not the same as P cross Q. And so given that the order matters, it's always the first vector and then the second vector. Okay, so what if we want to take the moment of a force about some point? Okay, so we have our floating potato, right? And you have this force is being applied on the outside of this potato, and we're curious, what is the moment that this force is creating about the origin of this potato? Okay, well, the moment of a force is defined as the moment, which is a vector, is r cross f. That is the thing that you are going to hear over and over and over in this class. Moment is r cross f. The moment vector m0 is perpendicular to the plane containing O and the force F, right? So again, we talked about how when you do a cross product, you know that the direction of that vector is perpendicular to the plane containing these. So you have r and f, and the moment vector is perpendicular to that at that point. The magnitude of m0 is a measure how much the force wants to rotate the body. Okay, that's the moment, right? That's what we all understand the moment to be. Moments, a lot of times people refer to them as a torque, right? It's how much does this want to rotate a body? And it can be determined with this equation. m0 is rf sine theta. Or, hopefully, r sine theta is what? R sine theta is the perpendicular distance from the point that you care about to the force, to the vector along where the force is applied. So moment can be written as force times distance. But again, this moment is a vector. A moment is a vector. This is the magnitude of the moment is given as the force times distance. And the sense, or the sign, right, is found by the right-hand rule. So in this case, if the force is here, it's r cross f. So you point your fingers in this r direction and then close your hand towards the f, and you will find that it is in the positive direction. Okay, any force F that has the same magnitude and direction, any force F prime that has the same magnitude and direction as F is equivalent if it also has the same line of action and therefore produces the same moment. So what it's saying is if you have this force F, if you apply this force F here, if it has the same magnitude and direction, and if it's on this same line of action, it will be equivalent because it'll have the same, it'll produce the same moment. Okay, so if we want to take the moment about a force in 2D, okay, so moments, when you do a moment, it's a cross product, r cross f. A cross product always has the vector that's perpendicular to the plane that contains r and f, right? And so what does that mean? The moment vector will always be perpendicular to the plane, or out of the piece of paper, out of 2D. So for the discussion of moments, when we're talking about a 2D structure, right, so it has length and breadth, but it doesn't have any depth. And if the subject is only subject to forces in xy, so in other words, when we're talking about typical xy problems, the plane of the structure contains the point O and the force F. So therefore, the moment is perpendicular to that plane. In other words, the moment is sticking up out of the page. Okay, but that's a little bit it's a little bit off, right? Because this is a 2D problem, and a moment is inherently going to be in the third dimension. So what we're going to do is we're going to say forces that tend to rotate the structure clockwise have a negative sense. So if it goes this way, we're going to call this a negative moment. And forces that tend to rotate the structure counterclockwise, we're going to call positive. Now you can imagine where this comes from, because if the positive z-axis is sticking straight up out of this paper, then this one, in order for that to happen, in order for to right-hand rule, you're going to be sticking your thumb into the paper, so it's in the negative z-axis, and here you're going to be sticking your thumb out of the paper, which is positive z-axis. And so that's how we're going to find moments for 2D. Clockwise, we're going to count as negative, and counterclockwise, we're going to count as positive. Now, having said that, a lot of times, quite frankly, I will just want you to write the moment is equal to this and then put an arrow like this or an arrow like this, just to clearly differentiate so there's no confusion there. Okay, Varignon's theorem. I think that's how you say his name. Honestly, I'm not sure. It says the moment about a point O of the resultant of several forces is equal to the sum of the moments of the various forces about the same point O. So what in the world is that saying? Okay, this is actually hugely helpful. I know it doesn't sound like it, but it's actually hugely helpful. So what is this saying? That the moment, so if you do a r cross f1 plus f2 plus f3 and so on, it is the same thing as just saying r cross f1 plus r cross f2 and so on. So here we have this point A. You have, in this case, 4 forces acting on this. Okay, the moment of about the point O of these 4 forces, you can either do r cross f1 plus r cross f2 plus r cross f3 plus r cross f4, or you could figure out the resultant of these 4 forces, call it r, that's an unfortunate name, but call it the resultant, right? We'll call it just f, generic f, that f is equal to the sum of all of the separate forces. Well, then that moment is also just r cross f. And this is especially helpful when we're given x, y, z forces, because you can just figure out the x component of things, the y component of things, and the z component of things, and then you can deal with the moments individually. So this Varignon's theorem is extremely helpful. Okay, let's look at the rectangular components of the moment of a force. Okay, the moment of a force F about the origin. Okay, so if we have this force F, right, we have the x, y, and z components of this force. We just talked about Varignon's theorem, right? So if we have some force F, we can break it into individual parts, or we can take all these individual parts and make it into one force F. They can go both ways, right? And so the moment of this force is always going to be r cross F. That's just what a moment is. Where r is from here, from the point that you care about to the point that the force is being applied. So r in this case is going to be x, y, and z. So our r is x in the I direction, y in the j, z in the k direction. And our forces are fx, fy, and fc. So given that as our moment, how do we go through and calculate this? Well, we say the moment is r cross f. So we have our r and we have our f, and you go through and we do the determinant, and you just figure it out. It's the I component times, so I and then this minus this. The way I do determinants is I say I and then this minus this, and then I say minus j and then this times that minus this times that, and then plus k, this times this minus this times this. Everyone does determinants a little bit differently, and honestly I don't really care how you do it. If you have any questions, come talk to me. But that is how I do the determinants, and so that's when you see me doing it, that's what I'll do. I, that times that, minus that times that, minus j, so that I always go top left, bottom left, top right, and then plus k, top left, bottom left, top right. And that gives you this answer right there. Okay, now let's consider taking the moment about of a force, determining the moment of the force about some arbitrary point B. Okay, this is really not very different than what we just did before. Moment is what? The moment is always and will always be r cross f. But in this case, the only thing that's different about this, and here we were taking it about the origin to here. Now we have it about some other arbitrary point B. The only thing that changes is how you define r. Okay, so moment is r cross f, always, always. F is still just the x, y, z components of f, right? It's just a vector, force of the x in the I direction, the y component in the j, and the z component in the k. Now the difference is we have to define what r is, and here is our r. What is r? Well, it's just basically x2 minus x1, y2 minus y1, z2 minus z1, right? So our r is go a certain amount in the x direction, a certain amount in the y direction, and a certain amount in the j direction. And that certain amount is the difference between the x component of a and b, the difference in the y component of a and b, and so on. And so you end up with your r vector. You define your r vector nice and clearly. xa minus xb times I plus ya minus yb times j plus za minus zb times k. F is still f, and moment is still r cross f. So you still have you create the determinant I, j, and k, and then you have your r vector. And again, the difference is now it's defined slightly differently, but it's just the r vector and the f vector, and you just simply do the determinant. So really doing it about any arbitrary point is really no different at all. You just have to define your r appropriately, and we're going to do this a lot in class, so make sure that we define our r correctly. Okay, now let's talk about kind of a simplified case, the 2D structures. For a 2D structure, what do you have? Moment is what? It's always r cross f. That's the deal. Moment is r cross f. But if the stuff exists only in, say, the xy plane, the cross product is always perpendicular, right? So the moment is going to be in the z-axis. So this is absolutely true. The moment vector is in the k direction, in the direction of the z-axis. However, when it is two-dimensional, we know the direction. So usually we will only talk about the magnitude of the moment. We don't talk about it as a vector so much as a magnitude. And so we're going to say, hey, the magnitude of the moment is the z component of it, right? And it is what? Well, if you do the determinant, you can figure this out. But on kind of a simpler level, the way I think about this is it's just your x component of your force times the y distance, and the y component of the force times the x distance. So when do you subtract them? When do you add them? Well, you look at this one, right? This force about this point is going to want to make it rotate in this direction. This force about this point is going to want to make it rotate in that direction. So these are going to have the opposite signs. Same thing holds true if you're doing about some other arbitrary point instead of about the origin. Again, it's the same thing. The r, you define your r appropriately. Now r is not from the origin, it's from point B, but you still end up with the xa minus xb and whatnot. And it comes down to the same thing. This force times this distance. Well, this distance now you have to define it. You have to include the b portion of the y. You know, the y portion of the point B, and so on. But the idea is exactly the same. It's just this force times this distance, and this force times this distance. So you'll hear me say this a lot. It's, you know, the x force times the y distance and the y force times the x distance, and then you account for the signs appropriately. Okay, let's do some examples. Example 3.1, example 3.4.